Hello dear students, we are discussing about the rectifiers, and in the previous class we have studied about half-wave rectifier, right? Where we have seen the circuit as well as its operation. Okay? And also we have seen the waveform. Now we'll be studying its important concepts like peak inverse voltage for half-wave rectifier. This we are going to study with respect to the half-wave rectifier. Okay? So we are going to study peak inverse voltage. Okay. So what is this peak inverse voltage for half-wave rectifier? HWR, half-wave rectifier. Okay. Peak inverse voltage. Right. So what is this peak inverse voltage? First of all, it is the maximum voltage applied to the rectifier rectifying diode. Okay. Or reverse bias. Yeah, when it is under reverse bias. Okay. So this is the circuit we have seen in previous class. It is having one diode like this and a resistor. And here we are going to observe the output. Okay, so this is RL, this is diode that turns on for forward bias and it will be turned off for reverse bias. So what happens? For the forward bias, it is just acting as a closed switch, so the current is going to flow through the load resistance RL and it is going to create a positive half cycle in the output. Right? This is clear about the positive half cycle. But what happens in the negative half cycle? For the negative half cycle, this diode is not conducting, it is reverse biased now. Okay, it is not going to be turned on, it is now acting as an open switch. Okay, so this diode is not allowing any current to flow through the resistor. So this resistor is not observing any current through it. Here, so there is no current flowing through the resistor, so no voltage drop across the resistor RL. There is no voltage drop across the resistor RL. So whatever is the value of the maximum voltage, and it's a secondary, whatever maximum voltage Vm it is having, the entire voltage is applied to the diode. Okay, the entire voltage will be applied to the diode. That means the secondary maximum voltage called as Vm. So the secondary maximum voltage is the peak inverse voltage for half-wave rectifier. So if IB is equal to nothing but Vm. Right? Yeah. So whatever secondary voltage, maximum secondary voltage Vm, the peak value of the secondary voltage Vm is the maximum voltage that is applied to the diode under reverse bias condition. That's why Vm is equal to PIV. So this is the maximum voltage that reaches the diode under reverse bias condition when the diode is not conducting. Right? So this is called as what? Peak inverse voltage for half-wave rectifier. And peak inverse voltage for half-wave rectifier is given by Vm. PIV is equal to Vm. Right? It is the maximum voltage applied to the rectifying diode for reverse bias when it is not conducting, when it is off. Otherwise, when it is open switched. Right? In that case, whatever maximum voltage is applied to the diode is called as what? It's a peak inverse voltage because it is applied in the reverse bias condition. That's why inverse peak maximum value. Okay, voltage Vm because it is a form of voltage. That's why PIV, peak inverse voltage is Vm. So this is the maximum value of voltage that will be applied to the diode when it is not in conducting form, when it is reverse bias, when it is when it is not conducting or it is acting as an open switch. Yeah. So this is about the peak inverse voltage. Peak inverse voltage is given by what? Vm. Right? So now we know that the peak inverse voltage for the half-wave rectifier is what? Vm. Right? Half-wave rectifier peak inverse voltage. PIV is equal to Vm. This much you need to remember always. Okay. So peak inverse voltage for the half-wave rectifier is given by Vm. Right? Now we will look into the RMS and average values for the load voltage. Right? We are talking about the load voltage. See, this is the waveform. So the waveform is basically having only positive cycles. B in, B out. Right? So this is the positive cycle that we observe, and we are writing the RMS average values of voltage and current. Average values of voltage and current and RMS values of voltage. Okay. Average and RMS values of voltage and current. Right? And that is for the load voltage. That means this portion. This is the input part and this is the output part. So we are looking at it with respect to all these average and RMS values are for the rectified form of the output, rectified output. Right? So first we will see what are the average values. So here we will see V average, where V average is given by, normally it is given by M by pi, but here it will be Vm by pi. Okay, it is going to be Vm by pi. Why Vm by pi? 2 Vm by pi was the expression for an entire cycle because it was having positive and negative cycles. So it was, so as I had told you while calculating the average value that as there are two cycles, right? So the average of the two cycles is going to be 0, right? Because for every positive value there is a corresponding negative value. So each values are going to cancel out each other. Then we are going to result into a 0 average value. That's why normally what we do, we take Vm twice divided by pi for what we can say, a normal cycle which is having two half cycles. But here, what we observe in the voltage, this is called as load voltage, right? We can write it as VL. Output V naught, otherwise the load voltage VL. Okay, so the low voltage is having only positive cycle, whereas the negative cycle for the entire waveform is just eliminated, right? So this positive cycle, here also positive cycle, there are only positive cycles, that's why it is given by Vm by pi. Right? It is given by what? Vm by pi. Clear? So what is the I average value? I average value is equal to Vm by pi into Rn. Otherwise simply it is In by pi. Here, Vm by Rn is Im divided by pi. So these are the average values of voltage and current. Average values. Right? So these are the average values of voltage and current for a half wave rectifier. Here, this can be also written as I average is equal to V average. Okay, where V average is again Vm by pi means the same divided by RL. Okay, V average divided by RL, otherwise Im by pi. This forms Im, this forms it V average. If you consider it as this portion, it becomes V average. That is Vm by pi is V average, V average, RL is there divided by RL. If you consider this portion, Vm by RL is Im, pi is left, so Im divided by pi. You can form the expression in this. Yeah, so all the three expressions are correct for the I average value current. So this is the average value of voltage and current for half wave rectifier. So the average value of voltage and current for half wave rectifier is what? It is Vm by pi for V average and Im by pi for I average. Otherwise, V average by RL or Vm by Im by pi. Right? So these are all the expressions for the average values of voltage and current. Now we'll be studying the RMS values. So this is with respect to the load voltage we are studying. Okay, these are the values for the load voltage. That is having only positive cycles. There are no negative cycles existing. Okay, so RMS value of the voltage and current. RMS values of the voltage and current for load voltage. That is the output VL. Okay. So here we will see it is for the load voltage and these RMS values and average values are for the only positive half cycles. It is not for the entire cycle. Right. So VRMS is equal to Vm by 2. Okay, and this Vm is for the positive half cycle. This Vm. Okay. So Vm by 2. Where we have observed Vm by root 2, but here as there is only one cycle, it becomes Vm by 2. Whereas IRMS is equal to simply Vm by RL 2RL, otherwise just Im by 2. Okay, where Im is Vm by RL. That we have already seen in the previous example also. So these are the RMS values, okay, for voltage and current. Here, these are the RMS values of voltage and current. Where this is the RMS value of the load voltage, this is the maximum value of the load voltage. This is RMS value of the load current, and this is the maximum value of the load current. Okay, RMS value and maximum value of the load current. So all these parameters, voltage and currents, are with respect to the load voltage. Yeah, it is not with the input complete sine wave. It is with the only positive cycles. It is called the VL, load voltage. All these values of average and RMS values are with respect to the load voltage. Yeah, that is the output. Okay. So 1 by pi. So the average value V average is also called as what? VDC. Okay. VDC. Why VDC? Because we are considering it for the load voltage, and load voltage is considered to be a converted form of AC into DC. That's why we consider also to be VDC. When VDC is given by this, we have seen VM by pi, and I average is also called as IDC, where it is called as IM by pi, or otherwise V average by RL, right? Otherwise VM IM by, sorry, I average is equal to, so it is, can be written as VDC. Okay, as we have seen, V average is nothing but VDC. Why we are considering it to be VDC? Because it is the converted form of the AC signal into the pulsating form of DC. So now we can call this as a DC signal, right? And the average values are, well, average values of voltage and current for DC values we are writing. That's why we call it as VDC and IDC. Here, right? Okay. So this is about the RMS values and RMS values of voltage and current for load voltage of half wave amplifier, right? Now we will see the next two important terms here and the expressions for ripple factor and efficiency, which is very important. So, ripple factor. So I have told you already what is ripple. It is the presence of AC still in the rectified form of DC. Okay. Presence of AC is still in the rectified form of DC, and that is called as what? Ripple. Now what is this ripple factor? Ripple factor means it is going to give a mathematical term of how much ripple is present in that signal. Right? And it is given by the ratio of RMS value of the AC input component, otherwise signal, to the DC value or average value of load voltage. Load DC value of output or load signal or component. Okay, it can be with respect to the voltage or it with respect to the current when we are considering it as a signal or a component. Okay, if I write it as the ratio of the RMS value of the AC input voltage to the DC value of the output load voltage, then it is with respect to the voltage, right? And this is represented by gamma. Okay, it is represented by what? The symbol gamma, and it is given by under root IRMS, So I am writing with respect to the current. We can also write it with respect to the voltage. So IDC whole square minus 1. Okay. Okay. IRMS by IDC minus 1, and its typical value is 1.21 for half wave 25. Here 1.21 for half wave rectifier. For half wave rectifier it is 1.21, and definitely it will reduce for the full wave rectifier because the ripple content is going to be reduced. Okay. Here. So this is the ripple factor, and ripple factor is the presence of the AC. Ripple is basically the presence of the AC still in the rectified form of DC. The rectified form of DC in the case of half wave rectifier is not still in the complete form of DC. It is still having variable values. Okay, that's why what it is called ripple is the presence of AC in the DC equivalent signal of the converted form, right? And that is defined as the ratio of the RMS value of the AC input component, okay? AC input voltage also is considered to the DC value of the output load signal, okay? Here, so this is about the ripple factor, and typical value 1.21. You have to remember this value 1.21. It is a unitless quantity. So ripple factor gamma is given by 1.21. The typical value of the ripple factor for half wave rectifier. Okay, for half wave rectifier is 1.21. This is a very frequently or commonly asked question in 1 mark. What is the ripple factor for half wave rectifier? 1.21 is the answer. Here. Now we will see the efficiency. Efficiency is usually a ratio of output to input. And what is the output in this case? The output in this case is the DC value, whereas the input is the AC value. Right? So efficiency is normally a ratio of output to input. Efficiency represented by this is efficiency. Efficiency represented by eta. Okay. And it is normally a ratio of output to input, and here the ratio output is a DC and input is an AC. That's why efficiency is basically the ratio of output DC power to the input AC power. Okay, so this efficiency is expressed in the form of output and input powers. Here, DC power and AC power. Here, and it is given by PDC by PAC. PDC by PAC, and its typical value is 40.6%, otherwise 0.406, which can be written in terms of percentage. So this into 100% is going to give you 40.6%. Okay, so eta is equal to 40.6% for half wave rectifier. So these are all the important expressions or terms for the half wave rectifier. So what all we have studied for the half wave rectifier? We have seen its peak inverse voltage, where peak inverse voltage is the maximum voltage that is applied to the rectifying diode when it is not conducting, and it is given by Vm. VIV is equal to Vm for half wave rectifier, right? After that, we have seen the average values, that is DC values and RMS values for the load voltage. Yeah, and that is given by what? It is given by for V average or VDC is equal to Vm by pi. Why only pi, not 2 Vm by pi? Because we are having only one half cycle. The other half cycle is not existing. That's why only Vm by pi, not 2 Vm by pi. Right? VDC. IDC is equal to similarly Im by pi. Right? Next, we have seen the RMS values where Vrms is equal to Vm by 2, not root 2, because again there is only one half cycle. Okay, clear? And Irms is equal to Im by 2. And we have seen the ripple factor. Ripple factor is the ratio of RMS value of the AC component to the DC or average value of the output DC component. Right? It is given by under root IRMS by IDC whole square divided minus 1, and its typical value is 1.21 for half wave rectifier. And also we have seen the efficiency, where efficiency is the ratio of output DC power to the input AC power, PDC by PAC, and that is 40.6% for half wave rectifier. These are the typical values for half wave rectifiers. Here, now we will move to the next rectifier, that is a full wave rectifier. So again, to understand the center tapped full wave rectifier, it is essential to understand the center tapped transformer first. Okay, the entire operation is depending on the operation of the center tapped transformer, right? So the next topic is the full wave rectifiers. So now we have completed the half wave rectifier. Now we are moving into the full wave rectifier, where the first rectifier we will be studying is the center tapped Okay, full wave rectifier. Center tapped full wave rectifier. It is having an primary part that is applied with the AC input. Right, followed by a, this is the primary part. Now we're moving into the secondary part. Center is tap. Okay. This is the circuit for center tapped full wave rectifier. This is the load resistor RL. This is the output. Right? So this is the diode V1 and this is the diode G2. Right? And the center is normally at ground. Center is normally at the ground, that is always at a zero potential. Here, with respect to the center, there are two terminals, A and B. Here, this is the circuit diagram for full wave rectifier, center tapped full wave rectifier. Here, this is the circuit for center tapped full wave rectifier. This will be the AC signal that will be applied to the rectifier. So I will just give you a brief about this center tapped transformer first. That will be having two similar or equal magnitude signals but with opposite polarity, otherwise 180-degree phase difference. Okay. What does that mean? For every positive cycle of the AC input, the terminal A will be having positive cycle and negative cycle with respect to the AC. So with respect to the AC input, the terminal A. So basically the center tap transformer is having two different voltages of same magnitude. That means VM value is the same. So A and B are having the same values, right? But they are out of phase. Otherwise, one is positive, the other is negative. When the other is negative, the other one has to be positive, right? So for the positive half cycle of the AC input, whenever during the positive cycle of the AC input, the terminal A is positive cycle, whereas terminal B is negative cycle. Here, terminal A is having positive cycle, whereas B is having negative cycle. For the negative cycle, this becomes negative cycle and this becomes positive cycle. Okay, so they are working alternately. When this is positive, this is negative. When this is negative, this is negative. This is going to be positive. Okay, so A and B are just the opposite, but with same value of AC signal, that is VA, right? Here, so this is the simple concept. For the positive half cycle, A is positive. For the negative half cycle, B is positive. Okay, when A is positive, B is negative. When B is positive, A is negative. Simple. Here, right? So, what happens now? For positive half cycle, for positive half cycle, what happens? The diode, this is a positive cycle. This diode turns on. Okay, I am just showing it by a closed switch. Right? The remaining circuit is as it follows. And this is the output. This is RL. Here, now what happens? This is applied with the positive cycle, there is no negative cycle, positive cycle is applied. So this positive cycle reaching the A terminal and a negative cycle reaching the B terminal. Okay, so this A terminal, the positive cycle at the A terminal forward biases this diode and this acts as a closed switch. Okay, whereas this negative cycle at the B for application of positive cycle we are talking. This reverse biases the diode and this diode is open switch. Here, no, this portion of the circuit there will be no flow of current, whereas here the current flows. Okay, current I flows, and this current flows like this through the resistor in the direction It is called as IL. Okay, and the voltage is dropped across the output PL and it forms a positive half cycle. Here, and this is for the application of the positive cycle. This is for the application of the positive cycle. What is going to happen within the circuit, right? Now we will see what happens for the negative half cycle. Is applied with the negative half cycle. Okay, this is now reverse biased by for the negative half cycle A is receiving the negative half cycle, whereas B is receiving the positive half cycle. Here, and this will be acting as a closed switch now, right? This cross means that this portion is not connected, it is over that line. Okay, so this is directly connected to this part, it is not connected to the ground here. Okay, here. So now what happens? Where we can observe the load voltage, this is the RL through which the IL flows. But how? Because this diode is off, okay? So this diode is turned off, there will be no current flowing through here. But this diode, the second diode D2, okay, this is D1 that is closed, this is D2 that is open here, and here D1 is open, and D2 is closed now. So now due to the closed switch, otherwise the forward biasing of the diode D2, what is happening? The current is resulting from this portion of this secondary winding of the transformer. Here this D2 is forward biased, current flows like this, and it reaches the load resistance and forms a load current. And again, the current is in the direction from M to N. It is not in the N to M form, it is in the same direction. That's why it is going to form another positive side. Here. And together we can observe the output to be like this. And this is due to D1 and this is due to D2. Okay, this cycle we can observe at the output. This is the VL, right? The load voltage with respect to the time. Okay, so for the positive half cycle, D1 is conducting, and this positive half cycle is formed due to D1, and this is due to the conduction of the D2. So this is going to form another half cycle for the D2. Clear? So this is the overall output of the half wave full wave rectifier, whereas this is for the positive half cycle and this is the operation for the negative half cycle. So together it is going to form the entire rectified form of the cycle, where here we can see it will be continued for the entire cycle, and this is due to D1, this is due to D2, okay, again D1 and D2. Okay, here, so this is the simple operation of a center tapped full wave rectifier. So now I am going to guide the working of the center tapped full wave rectifier. First of all, during the positive half cycle, during the positive half cycle, what happens during the positive half cycle? The A terminal of secondary winding is positive. For the positive half cycle, A terminal is positive, that forward bias diode D1. Okay, here, whereas terminal B of secondary is negative, that reverse bias diode D2. That reverse bias the diode D2. Okay. So D1 conducts and D2 does not conduct. Okay, D1 conducts and D2 doesn't conduct. Okay, now D1 is conducting. Now what happens? As D1 is conducting and D2 is not conducting. As D1 conducts, a current IL flows through RL. Okay. As D1 conducts, a current IL flows through RL. Okay. Through RL, due to which a voltage VL is dropped across RL. Okay, the current flows in the direction from M to N. In the direction from M to N. Hence, a positive half cycle is formed at output. So this forms the positive half cycle. So this is the working for the positive half cycle. Working of the center tap to full wave rectifier for positive half cycle. So what they are saying, during the positive half cycle, the terminal A is positive for the positive half cycle, the terminal A of the secondary winding is positive, that forward bias D1. This is on. Whereas terminal B of the secondary is negative, that reverse bias D2. Okay. So as this is forward bias, this is reverse bias, D1 conducts and D2 doesn't conduct. This is off, this is on. As D1 conducts, a current IL flows through RL, due to which a voltage VL is dropped across RL. Okay, the current flows in the direction from M to N. Okay, so this ion flows in the direction from M to L. Hence, a positive half cycle is formed at the output. Positive half cycle is formed. Yeah. So this is the simple explanation of the working of center tapped full wave rectifier. Now what happens for the negative half cycle? I will just edit this portion only. During the negative half cycle, the A terminal of the secondary is negative. Is negative. That reverse bias. Reverse bias diode D1. Whereas terminal B is positive. That forward bias. That forward bias diode D2. So D2 conducts whereas D1 does not conduct. Clear? So this by little modifications in the sentence we have converted this into a working for negative cycle. So what happens during the negative half cycle, the A terminal of secondary winding is negative. That reverse bias diode D1, right? Whereas terminal B of the secondary is positive, that forward bias diode D2. So D2 conducts and this is and D1 doesn't conduct. Okay, D2 conducts and D1 doesn't conduct. Now, as D2 conducts, a current IL flows through RL due to which a voltage VL is dropped across RL. The current flows in the direction from M to N again in this case also. M to N again in this case also. Hence, a positive half cycle is formed at the output. Yeah, right. This I have explained with the circuits also in detail. I have already explained. So this is the working for negative half cycle. Right? So what it says in the negative half cycle, during the negative half cycle, terminal A is negative, that reverse bias D1, whereas terminal B is positive, that forward bias D2. D2 conducts, D1 doesn't conduct. As D2 conducts, a current IL flows through RL due to which a voltage VL is dropped across RL. Okay, and this VL voltage drop VL itself is the output. Okay. The current flows in the direction from M to N, in this case also, in negative cycle also. Hence, a positive half cycle is formed at the output. How this flows from M to N, I have explained already with respect to the circuit diagram. Why it is in the same direction, M to N, in both the cases, I have explained with circuit itself, how it happens. Here, so there should be no doubt about how in both the cases the current is flowing from M to N only. Now we will see the waveforms of full wave. Waveform of full wave rectifier. This is the input signal. V in, VL, P. Here. This is the output of the rectifier. Okay. So this is VL, and this cycle is resulting due to D1. This is resulting due to D2. Again due to D1 and again due to D2. Right? So this is the output for the full wave rectifier center tapped. Center tapped full wave rectifier. Right? Similar, we will be looking for the bridge rectifier, but the operation and the circuit entirely differs for the bridge rectifier. Yeah? So in the next class, we will be covering the bridge rectifier and also the average value, RMS value, ripple factor, and efficiency for the full wave rectifiers. Right? So as it is with respect to the load voltage, and the load voltage is similar for the center tapped or bridge rectifier. So we are considering the RMS value, average value, and ripple factor and efficiency hold together for center tapped as well as bridge rectifier. Okay. So common discussion of the RMS value, average value, ripple factor, and efficiency will be done for full wave rectifiers, center tap as well as bridge. Here. So this is about the center tap full wave rectifier. Entire explanation. It's working for the positive and negative half cycle, whereas the waveforms. Okay, output waveform and input waveform for the full wave rectifier. Here. So in the next class we'll be looking for the bridge rectifier, and also I have told you RMS values and average values of the load voltage. Right. So this is center tapped rectifier. Next we will be studying the bridge rectifier, where basically it will be comprising of 4 diodes, and we will be also having a comparison of center tapped and bridge rectifier. Yeah. So how it works, I will just revise this. Input signal, AC input is applied for the positive half cycle of the AC input. For the positive half cycle of the AC input, terminal A is positive, is having positive half cycle. Terminal B is having negative half cycle. So this positive half cycle at the terminal A forward bias the D1, whereas the negative half cycle at the terminal B reverse bias the D2. So this much portion is simply removed. This much portion is not applied to the circuit. So what happens? The current flow resulting due to the D1 simply travels like this and it passes through the RL. Here, when it is passing through the RL, it is traveling in the direction from M to N, that forms a positive half cycle, and the output is just the voltage drop across the RL. Whatever the value of voltage drop is observed in the RL, that is going to appear in the output. Here, now for the negative half cycle, what happens? For the negative half cycle, what happens? The terminal A is now observing negative cycle, whereas the terminal B is observing positive half cycle. So, for the negative half cycle of the AC input, terminal A is having negative half cycle, that reverse bias the diode B1, and terminal B is having positive half cycle, that forward bias the B2. Now, as this is reverse bias, this much portion of the circuit do not exist. So the current starts from this terminal, from the secondary here, from the B, it moves to the diode, and from the diode it is going to reach here to the M. Like this the current flows, and from the M it is going to reach the N terminal. So in this case also the current is flowing from M to N through the load resistor RL, and the current is IL. Due to the current flowing through RL, there will be a voltage drop across the RL, that is called as VL, and that VL is resulting due to what? This diode D2. Here, resulting due to the diode D2. Here. So this is the operation. Due to D1, this positive cycle is formed. Due to D2, this positive cycle is formed. So this is the entire operation for positive half cycle as well as negative half cycle of the central tapped full wave rectifier. Very important for exams. Very often you asked it for 5 marks. Okay, it is kind of fixed question that can be asked in the exams for 5 marks, as it is very important. So in the exams, you have to draw the circuit, you have to write the explanation for the positive half cycle, for the negative half cycle, and this waveform that is showing input as well as output waves of the rectifier. Right? So this much, along with the explanation, the circuit and that waveform has to be drawn when this question is asked for 5 marks. And the question will be asked, explain the working of central tap, the full wave rectifier along with its circuits and waveform. Here, so for such question, you have to draw this, you have to explain during the positive half cycle, during the negative half cycle what happened, and finally the waveforms. Here. So also the bridge rectifier is important. Even the bridge rectifier could be asked in 5 marks. There also you have to draw the circuit, explanation, and waveforms. Okay, so that will be discussing in the next chapter. Sorry, in the next coming class. Okay, the bridge rectifier, right? So what all we have discussed in today's class about the half wave rectifier? We have discussed its average value, RMS value, ripple factor, and efficiency. Right, and then we have discussed about the full wave rectifier, in which we have discussed in the center tap to full wave. Yeah. So what we have seen, the peak inverse voltage for the half wave rectifier is what? Vm. Why it is Vm? Because the maximum voltage of the secondary during the negative half cycle, as the diode is off, there is no voltage drop across the RL. So the entire voltage of the secondary, the maximum voltage Vm, is applied to the diode only for the reverse bias condition for the negative half cycle of the half wave rectifier. Right? So that is the maximum voltage that is applied to the diode for when it is not conducting, when it is in the non-conducting form. Here, and PIV for half wave rectifier is given by what? Pm. Similarly, we have also seen the RMS value and average value, where average value are the DC value of the load voltage, V average, I average, given by Vm by pi, Im by pi respectively. Here, RMS values Vm by 2, Im by 2 respectively for voltage and current. Here, so these load RMS DC values, average values, DC values that are average values, and the RMS values are for the VL, the load voltage. And also we have seen the ripple factor and efficiency, where ripple factor is 1.21, typical value for half wave rectifier, whereas 40.6% of efficiency for half wave rectifier. Here, right? So we have discussed the important expressions for a half wave rectifier and the central tap wave rectifier in the next class. The further topic, that is the bridge rectifier, will be covering in the next class. This is all about today's class, students. Thank you.